Welcome back to chemistry and our big idea for this unit, which is ocean acidification. We specifically this week are looking at a gizmo that's called ocean carbon equilibrium. And I want to give you a quick review of the problem that they're giving you in that gizmo. So it turns out that the mussels in the Arctic Ocean are not doing so hot. They have found out that mussels are eroding or dissolving faster than they're able to form. And it's probably due to the fact that they're not getting enough calcium carbonate from the ocean. So in this introduction part of the gizmo, they have you take a look at a healthy part of a, of a mussel shell. And you notice that it's smooth, there's no bumps, cracks, ridges, whatever. But then the eroded part is because there's normal wear and tear with the shell, and the calcium carbonate that it's made of just naturally dissolves away. But what they're finding out is that this nice shape of a shell is actually not the same shape that we're seeing now. There's irregularities in its formation that mean, it's not as big, it's not as strong, and it's just not a healthy mussel. If we look at the erosion data starting from 1995 to the year 2020, there's been a pretty significant increase in the amount of shell erosion of these mussels. We jumped from having only 10%, which is normal wear and tear of a mussel shell, all the way up to 40%. And this is probably just going to continue increasing. So how do we figure out what's going on with this problem and how do we solve it? We started looking at the handbook part of this gizmo, and we looked at, in particular, the ocean carbon cycle. I'm going to kind of jump ahead and then go backwards here. Perfect. So this is a image that shows all of the reactions that we were looking at. It started with the absorption of carbon dioxide gas into the ocean, and then it followed a series of reactions that takes carbon dioxide, reacts it with water to form carbonic acid. Carbonic acid can dissolve or break apart in the ocean to create molecules like bicarbonate or carbonate. All of those reactions release hydrogen ions into the ocean, and that was where we paused and we thought, well, maybe that's kind of the reason why we're seeing ocean acidification. But ultimately, we said that carbonate ion that's formed is really important because it can bond with calcium ions to create the calcium carbonate needed to build shells for marine organisms. Today, what we're going to do is take a closer look into the idea of solubility and reaction rates. And this is going to tie directly back in with this big word we learned yesterday or the day before that's called equilibrium. All of these reactions here are in equilibrium, which means that they are reversible reactions and that the forward reaction is happening at the same rate as the reverse reaction. What that ultimately means is that the products and reactants are all in the same concentration all the time. So we're going to go ahead and jump into this. We're going to jump into that solubility part and take a closer look. So it says calcifiers. Remember, calcifiers are the organisms that use calcium and carbonate to build their shells. Oh, look, that's exactly what it says. The calcifiers use the calcium carbonate ions to make the shells. These ions, though, become solid in the shell. So this is an interesting thing just to wrap your brain around. Carbonate is aqueous, which means it's dissolved in the ocean water right now. It's going to react with other calcium ions that are in the ocean water. And when those two combine, that's when it forms a solid compound called calcium carbonate. All right, so it goes from two aqueous ions into a solid one. Click next. It says the ability of calcifiers to make their shells out of calcium carbonate depends on the concentration or the amount of calcium and carbonate ions in solution. If we look at solubility, it says calcium carbonate is not very soluble in water. However, it is soluble enough for animals to use to make shells. Now, what's that word soluble mean? It says how soluble a substance is describes its ability to dissolve in a certain solute. And I think the best example of solubility is putting salt or sugar in water. You add a teaspoon of it to a cup of water, you stir it up, and it dissolves, right? You see it as it becomes a clear solution. It disappears. That's solubility, the ability to dissolve. So it says calcium carbonate is not very soluble in water, which means it doesn't dissolve very easily in water. However, it is soluble enough for animals to use to make shells. It says if calcium carbonate was more soluble in water, like leaning towards the salt and sugar and water type of scenario, the shells would dissolve quickly back into the ocean. So think about that. If these shells are made of calcium carbonate, but calcium carbonate dissolves really easily in water, then those shells would just dissolve away, right? And that's not a good thing. The shells want to be there to protect the organism. If calcium carbonate was not soluble enough, meaning it won't dissolve in water, then there wouldn't be enough calcium or carbonate ions to actually make the shells. Okay, so there's two scenarios here that are at play. We have one where it's too soluble and we're adding lots of calcium ions and carbonate ions back into the ocean water. There's another scenario where because it's not soluble enough, notice the difference in concentration of those ions. There's not enough in the ocean water to actually make calcium carbonate anymore. So there needs to be a balance. It says solubility depends on the balance between dissolution and precipitation. It says the solid calcium carbonate dissolves in the water to become ions, and that's the process known as dissolution. The way I remember that is that dissolution sounds like dis going in the solution. Like this is going in the solution. Oh my gosh. If it helps you, it helps you. Dissolution is going into the solution, which means we're going from a solid version of calcium carbonate. We're going to turn it into a solution, which means we're going to dissolve it. We're going to break it apart into its calcium ion and its carbonate ions, and it's going to be floating around in the ocean water. That's dissolution. Now, like I said, there has to be balance, which means at the same time that that's happening, we need to be taking those ions out of the solution and turning them back into solid calcium carbonate. That process is called precipitation. Now, there's a chemistry joke that says like, you know the phrase, if you're not part of the solution, then you're part of the problem, right? Well, in this case, if you're not part of the solution, then you're part of the precipitate. Okay, so there's a chemistry joke, right? If you're not part of the solution, like dissolved ions in water solution, then you're part of the precipitate, which means you're part of the solid that has formed from solution, which in this case would be solid calcium carbonate. So again, there's a balance that happens between dissolution and precipitation. Now, coming back to the idea of reversible reactions, equilibrium, and now we've got these two other processes that we can name. How does that all work together? So dissolution and precipitation are in balance, all right? Now that is an example of a reversible reaction. It says every chemical reaction has a reaction rate that tells us how quickly the reaction happens. This means that we have a rate of dissolution, which means how fast these ions are being formed from the solid calcium carbonate. At the same time, there's a rate of precipitation, which means how fast are these ions able to form solid calcium carbonate. And because it's reversible, we need to think to ourselves, there's a forward reaction and there's a backwards reaction happening at the same time. All right. Key concepts. Number one, equilibrium, that big word that we learned previously, happens when opposing reactions happen at the same rate. So the rate of dissolution is happening at the same rate as precipitation. Because the rates are the same, they're going at the same speed, and we call that equilibrium. The next key concept, because the reaction rates are equal, the concentration of the ions stay constant. This is a little bit tricky to wrap your brain around. Because the rate of dissolution is the same as the rate of precipitation, the amount of calcium and carbonate ions that we have floating around in the solution are going to be the same. All right. The next one, at equilibrium, the reaction never stops. They just continue at the same rate. This is where I think a lot of people get a big misconception is that they think, oh, we've reached equilibrium, so we can just stop, like we can freeze time, keep the concentrations the same, and we'll just call it good. But that's not what actually happens. In equilibrium, those reactions are going in the forward direction at the same speed as the reverse direction, So it appears to us as if the reactions have stopped, but that's not really happening. They're going at the exact same speed, and so we just don't see any changes in those ion concentrations. So let's click next and see what the next part is. This one is going to go through some, I don't want to say it, it quantifies these ideas, which means we're going to add numbers to things. So it says we're going to use a beaker of water. That's shown here, and we're going to use some solid calcium carbonate to see how this reaction would work in the ocean. First of all, here's our reaction written as a full equation. We have calcium ions plus carbonate ions to create calcium carbonate. Notice the double-sided arrow like this means it's reversible. So we can run this reaction in the forwards direction. We can run it in the backwards direction. Down below, these are going to represent the concentrations of calcium and carbonate ions. The capital letter M stands for molar concentration, which means how many moles of these ions do we have per liter of water. Don't freak out about the units. You guys will go over that in AP Chem if you take that. The next thing that they're going to show you are the rates of the forward versus the reverse reactions. So the rate of dissolution, remember, think, oh, this is going into the solution, which means we're going from calcium carbonate into the ions calcium and carbonate. So this is the reverse reaction. Dissolution, the rate of dissolution is the reverse reaction. The next rate is the rate of precipitation, which is, you think, if you're not part of the solution, then you're part of the precipitate, which means you're going from the ion form, calcium and carbonate, and you're turning it into solid calcium carbonate. The difference between these two right now is that the rate of dissolution is going to be constant. It's going to stay the same. And the reason why is because we're going to have so much solid calcium carbonate sitting in our beaker that it's just going to constantly dissolve and produce these ions, calcium and carbonate. All right, so the rate of dissolution has a number and it's going to stay constant. What we're going to be measuring and focusing on is how does the rate of precipitation change as we're producing those ions. So we're going to do that by creating a graph. Let's just briefly overview the graph. We have time on the x-axis, which I know you can't really see it, but there's time on the bottom, and then there's your reaction rates on the y. Okay. It says initially the rate of precipitation is 0 because there is no solute, which means we haven't added calcium carbonate yet to the beaker, so there's nothing that we can actually measure. We haven't added calcium carbonate, which means we aren't producing calcium and carbonate ions, and so there's nothing for us to measure. All right, so it has to start at 0. But once we add calcium carbonate to this beaker, we're going to notice some changes. Notice again that the rate of dissolution is constant because we have all this solid calcium carbonate and just going to constantly be spewing out and dissolving and creating these calcium and carbonate ions in the water. But notice what's starting to happen to that rate of precipitation, which means the reverse reaction, or I guess according to this one, in the forward direction, taking those ions and turning it into calcium carbonate. So as we're producing ions in the water with this orange line, we're then taking them and running the reaction backwards, and we're creating the solid calcium carbonate. And that's happening more and more frequently as we're producing more and more of those calcium and carbonate ions. Let that sink in for a second. Okay. It says the salts dissolve to form ions. Those ions can now precipitate, so the reaction rate of the precipitation starts to go up. That's like what I just mentioned. And then eventually that rate of precipitation starts to slow down as we get near and close to the rate of dissolution. Eventually those two lines are going to meet, and at that point, the rate of dissolution is the same as the rate of precipitation. So the speed at which we are creating calcium and carbonate ions is at the same speed that we're taking those ions and turning them into calcium carbonate. Whew! Yay, science. All right, so let's digest the numbers a little bit. It says at equilibrium, the rates of opposing reactions are equal. So like I said, the speed at which we're dissolving into calcium carbonate ions is the same as the speed that we're taking those ions and turning it back into calcium carbonate. When the reaction rates are equal, the concentrations are the same. Okay, This is critical. All right, there's a huge misconception here. A lot of people think, oh, well, if the concentrations are the same, then the reaction must be in equilibrium. And that's the whole reason why. There's more to the story. You have to think past that and say, well, why are the concentrations the same? The concentrations are the same because the rates are the same. That's going to be important for you to remember. So at equilibrium, the concentration of the reactants and the reaction rates do not change, but the root cause is because of the reaction rate speeds being the same. That's why the concentrations are the same. This one I'm going to just kind of breeze over. We're not going to really focus on this part, but when the rate of precipitation and the rate of dissolution are the same, then we say the solution is saturated, which means we can no longer fit any more oh my gosh, I just lost the thing. We can't fit any more ions in the solution. There's just no space for it. But you have to keep remembering that when you get to that point, those ions are constantly in flux, right? They're turning into ions, and then the ions are turning back into calcium carbonate, and then they go back into the ions, and right? And so this process just keeps happening over and over and over and over and over again. Everything's in equilibrium, and so then we can call it saturated. Can't fit any more ions. They only have one option. They have to turn back into calcium carbonate. I don't know if you guys remember in middle school or elementary, you did this experiment where you had to add sugar to water, and then you'd heat it up, and then you keep adding sugar, and then eventually it would turn into a crystal when it cooled. That whole experiment deals with supersaturated solutions, and it's very similar to this. Okay, let's continue on. So, very good question that kind of reiterates one of the big ideas I told you about. Which set of values tells us if the reaction is at equilibrium? Is it A, the fact that the concentrations are the same? Is it B, something that we didn't even talk about? Or is it C, that the rates are the same? You might be thinking to yourself, all right, Ms. Billy, it's probably because the concentrations are the same. And remember, I said there's an underlying cause as to why those concentrations are the same. The reason why they're the same is because the rates are the same. The speed at which those reactions are happening are the same. Alrighty. I think this takes us to the end of our video here. What we're going to do in asynchronous time is look at Le Chatelier's, I think I said that right. I can never remember his name. Le Chatelier's principle, which is going to talk about equilibrium and what happens if we disrupt it, meaning what happens if we add more reactants, what happens if we're adding more products, and how are we going to keep equilibrium if we keep manipulating it, if we keep changing it. If you have any questions, let me know. If you need to rewatch this, go rewatch it. Otherwise, you guys do have access to this gizmo yourself, so you can go through and click on the solubility and reaction rate stuff, just like what I did, and take a look at it for yourself. Let me know what you